Hello, we're going to start talking about normal probability distributions. Say that 7 times in a row. So this is the first of 4 lessons we're going to take from the chapter of the book I'm using. We're not going to do the normal approximations to binomial distributions, so we can forget that. And here we go. Alright, we're going to do 2 things, and it won't take too long. We're going to interpret graphs with normal probability distributions and find the areas under those. Quick reminder, areas means probability. So you can put those 2 equal to each other. When you think of areas, think of probability and vice versa. We'll give a test mark here. Ready to roll. Alright, continuous random variables. Remember, continuous means there's no limit to the number of there's no limit to how many numbers you have between 0 and 3, for example. As opposed to the discrete ones where you have 0, 1, 2, 3, and that's it. But if you take 0 and 3, go halfway in between, and halfway in between that and 0, you know there's no end to that. So that makes it continuous. So the continuous probability distribution for a random variable, of course, we're going to pick something at random, and it's the most important one in statistics. So make a red underline on that one. This is what the graph looks like, and I would suggest that you get acquainted with drawing a lot of those, because we're going to draw a picture and then we're going to put things on the picture so we can help find those areas, probabilities, and so on. First interesting thing, right down here in the middle, or right up here in the middle, whichever way you look at it, find the mean, median, and the mode. They're all at the same place. The obvious one is the mode, because there's the most number of these, or more of these, than there are of those, or those, and they are less and less either way. It's bell-shaped, symmetric. Symmetric means you could put a mirror right in the middle, and if your mirror covered this side, you could look on one side of the mirror and see the second side of this curve. One side is the mirror image of the other. That's one way of saying about it. Another thing to keep in mind is that since it is symmetric, 50% of the area is on the left, 50% of the area is on the right. And the total area is 1 under the curve. Now remember, area and probability, you can put equals between those two in a way. And so since with normal or any probability distribution, the sum of the probability is equal to 1, that means the area under the curve is equal to 1. On both sides, that curve approaches the x-axis, both sides. Even if you went out in that direction 98,000 miles, it would be closer to the x-axis, but it never touches it. If you've taken some algebra before, you might recognize that as asymptotic nature. And in case you want to see this one, asymptotic. That means they get close to each other, but they never really touch. Next, between, remember this is the part right in the middle. This means this is moving to the left, one standard deviation from the mean. Mean minus standard deviation. And this one is to the right, mean plus one standard deviation. That's right in the center of the curve, and that should ring a bell, because that's 68% of the distribution right here. Remember that from the empirical rule? 68% there. You might remember that's 95% under that curve, and if you go out 3 standard deviations both ways, 99.7% of the area is between those two, here and here. Not only that, but you've got a pair of inflection points. Those inflection points are exactly one standard deviation in either direction from the center. And also, if you thought of this as a curve, suppose you're skiing from the top of this normal curved mountain. The inflection point is when you stop going down steeper and it starts to very slowly starts to level off. That's the inflection point. Next, the discrete one, the one we're leaving behind, can be graphed with a histogram. Probability density function. Remember, that's the one we used for where we had equals. Well, you can use the probability density function if you're going to graph a continuous one. It has 2 requirements. The area under the curve is 1, total area, and the function is never negative because probabilities are greater than or equal to 0. Next, it can have any mean and any positive standard deviation. In fact, the mean and the standard deviation are what separate any normal curve from any other normal curve. Sort of like the DNA for normal distributions. The mean gives the location of the line of symmetry. Remember that line of symmetry is right down the middle, and that's where the mean is. And line of symmetry means we can take this half, fold it over, and we'd end up with the left side. Standard deviation tells you what the spread is. The bigger the standard deviation, further apart this gets stretched. 3 small pictures. Notice that between this first one and the second one, the mean is the same, the standard deviation is different. In this one, the standard deviation is larger, so this is more spread out than this one is. The standard deviation, the smaller the standard deviation, the more squished it is. If you compare the last two, they have the same standard deviation, but the mean is different. And what the mean does is if you change the mean of a normal distribution, you slide that left or right. A positive mean slides it to the right, a negative mean slides it to the left. Well, not negative actually, but toward that direction. Which one of these has the greater mean? Do you remember? Well, if you take this first one, there's the mean on this one. There's the mean on this one. Which one has the greater mean? The one that has the mean to the right, which would be this one. Curve A. Which one has the greater standard deviation? The one with the greatest standard deviation is the one whose standard deviation is larger. This one, the B, is more spread out, so it has the greater standard deviation. Next, look at something in particular. We've got test scores from New York, and here's a normal curve. Draw that picture for yourself on your notes. What's the mean score? Okay, a little bit of luck here. Mean, first of all, is there. That's the easy part. But where exactly it hits down here is a little bit difficult to figure out, because this is just a graph. But you can get a pretty good idea. Mean would be wherever this comes directly downward, and it says estimate the standard deviation. Oh, remember, I just mentioned the standard deviation from the mean. Here's the mean. Standard deviation is where this thing stops getting steeper and starts leveling off just a little bit. So maybe something like this. And if that's the case, then if you can estimate this length to where it just starts leveling out, that will be your standard deviation on this graph. So I hope you try this for yourself. That's pretty hard. It's really tough. But the mean is about 305 and the standard deviation around 40. If you got anywhere close, you're probably fine. And the empirical rule we mentioned just a few minutes ago, 68% is between 1 and 2 standard deviations apart, 95% 2 standard deviations from the mean, and 99.7, almost everything is from a negative 3 standard deviations to a positive 3 standard deviations. Next. Okay, this is fun, meaning it's easy to. Now, I sort of just made. I call this the gold standard of normal distributions. Why do I sort of call it that? Because, again, I'm going to draw a picture. Here's my picture. Here's mean down the center. And this one it's absolutely gorgeous if you talk about normal distributions. 0 is right in the middle, just like the number line is. And if I come out here where the inflection point is, where it starts to level off on both sides, this standard deviation is exactly 1 unit to the right and 1 unit to the left, -1. That's the standard normal distribution. Has a mean of 0, standard deviation of 1. For example, now we haven't gotten to this yet, but you've seen some of those discrete normal distributions, and this is what one looks in your calculator. And I thought I'd just bring this up. Now, we don't use normal PDF. That's mostly for graphing. But when you do use the normal CDF, that's number 2 in your calculator, by the way. This first parameter is I goofed it up, I got it backwards. That's the lower bound of the area you're interested in. The second parameter is the upper bound. And if you're talking about the standard normal distribution, the last 2 parameters are 0 and 1. How nice is that? Not only that, speaking about the calculator, if you leave these 2 out, probably a bad practice. You should practice putting them in all the time. That way you don't accidentally leave them out when you can't. But if you leave those out, the calculator is going to assume a mean of 0 and a standard deviation of 1, which is okay if you're working with a standard one, but if you're not, you're getting the wrong curve and the wrong area. So here's our picture. Another reminder, the area under the curve, just like as if you were painting this whole thing blue, you would have to paint one, whatever you want to think of, 1 square mile, 1 square foot, whatever. It's an area of 1. Now, here's something you need to keep in your list of tools. The z-score you can find by taking any value, subtract the mean for that particular normal distribution, divide that by the standard deviation, and you've got yourself a z-score. It's as simple as that. And if the numbers are comfortable, you can actually do this without a calculator. So here we are, the standard normal distribution. 0 here, and if you see where it stops getting steeper and starts to level off, there's your inflection point on both sides. Same distance away from that center. 1 unit away to the right, 1 unit away to the left. That's your standard normal distribution, what I sometimes call the golden standard normal distribution. This slide we probably could do without, but if you look at one of these curves, or one of your curves, you'll notice that beyond about 3 or 3.5 standard deviations, there's almost no area out here at all. It's almost non-existent. It isn't, but it looks like it is. And the same on the left. Out beyond about negative 3.5, you'd have to have awfully good eyes to be able to see that there's any blue area out there, even though it does exist. The cumulative area increases as the z-scores increase. Now what that means is we're talking about jumping on our bicycle perhaps, or running from this side, and we're looking at the area as we're crossing, or going across this. As you get up to here, suppose you were adding up the area underneath that curve. The further you go, the more area is behind you, until up here, if you could go far enough, the area behind you would be a 1. That's sort of what they're getting at. A good reminder, because this can be handy, the cumulative area, and that means everything up to a certain point. In this case, we're talking about z equals 0. That's the standard mean. The area up to that point, where z equals 0, is 50%. Because it's symmetric. The left side and the right side are exactly the same, except mirror images. So the area is 0.5. And once you get out beyond about 3.5 standard deviations, that total area becomes very close to 1. Never 1, but mighty close. Now, Here's a question for us. What's the area that corresponds to a z-score of 1.15? So, just a reminder, the z-score, you take the score, subtract it by the mean, divide by the standard deviation, there's your z-score. That's how we got the 1.15. Now what? What's the area that corresponds to that score? What am I going to say? Draw the picture. There's the mean right in the middle. And since we're talking about z-scores, we're talking about the standard one. So 0 is right in the middle. The one we're talking about is 1.15. Second thing you have to do is, where is that? Well, if this is 0, then 1.15 is somewhere out here. You don't have to be accurate. Just get an idea of where it is. First thing you notice is that the cumulative area, which starts back here, would be 50% up to here, but you're going further. So this is going to be more than 50%. You don't know how much, but we're going to find out. And here's how you do it. So go to Stat, actually, a better way to do that is second distribution. Remember this, the bar is key. And then we'll get 2 normal CDF, not PDF. Don't accidentally get 1. Now we need the lower bound and the upper bound. So think of yourself as walking along here. Where do you stop adding up the area? 1.15. 1.15 is where you want to stop. Where do you start? Well, you start way back here. Way back here. How do you put that in the calculator? Way back here. Well, this is what I do. Just to make it easy to type, I could put maybe a -4 or a -5 or something, but just to make it easy and easy to type, I put in negative, make sure I put that in the negative, then I just put a bunch of 9s. 4 9s, for example. You can imagine how far out that is, way out. So this is essentially negative infinity for us, because this is the standard normal curve, so this is going to be way to the left. We're going to be missing almost no area if we start at -9999. Stop at 1.15, that's the upper bound. Since we're talking about z-scores, it automatically means the mean is 0 and the standard deviation is 1. So we'll put 0 and 1 in there, close it up, and we can hit our calculator. Do that in a second. Remember that if you don't put the 0 and 1 in there, it's going to assume it's 0 and 1. But also that can get you into a bad habit. So at least for a few weeks, even if it's 0 and 1, put it in anyway, just so you get in the habit of putting in a mean, putting in a standard deviation, because these two tell the calculator which normal distribution you're referring to. So second bars gives you the distribution, 2 for normal CDF, and they do it a little bit differently. I'm just giving you my interpretation or what I do, and that's what it looks like on the calculator. Sorry about the mess, but I think it's easy to follow. So this right here is where I put in the -9, 9, 9, 9. See, it's easier to type. Just make sure you put in the negative and just put a big number, and just hitting 9s over and over is an easy way to do it. And there is our area. And we should have expected that, because remember, There's where 0 is. There's 1.15. We know that up to here was 50%, so this is going to be more than 50%. And it has to be between 0 and 1 too. So this does make sense to us. Always give it that sanity check. Ask yourself just for a couple seconds, what do I expect to see? Okay? Next. So there's our area to the left of Z. What about this? What am I going to do first? I want the area that corresponds to a Z-score of negative 0.24. Yes, you guessed it, I hope. I'm going to draw a curve. Since I'm talking about Z's, that means 0 is right in the middle. And negative 0.24 means I'm back here somewhere. And the area I'm interested in is the area up to that point. Imagine you're painting that in. How much paint would that cost? Yeah, suppose, for example, that area of 1 counts as 1 bucket of paint. Maybe think of it that way. How much paint would you have to use? Well, notice that negative 0.24 isn't up to the 0. So we're not going to use half a bucket of paint or 0.5. It's going to be something less than 50% in the area. So, since it's the normal distribution, I'm going to go to second distribution, pick up normal CDF, number 2. I'm going to start as we usually do, and I'm going to do it my way, just because I think it's easy. And this time we want to start at negative 0.24, and it is a Z-score, so this is going to be a 0 and a 1, and since we're all just starting out, I'm going to put the 0 and the 1 in even though I don't have to. So what do I get? Remember, I'm probably expecting somewhere in the vicinity of 0.3, 0.4. We'll find out. So put those values in, and I guess I wasn't too far off. Just a little bit over 40% is our area. Not too hard. Remember, draw that picture. Sketch the normal curve. Yes, don't forget, draw the picture. Shade the area under the curve. That way you focus in on what the area is that you want the area for, that you want the number for. Find the area by following the directions for whatever case is shown. If you want the area to the left, find the area that corresponds to Z in the standard normal curve. If you want the area to the left of Z, then just for example, we go to normal CDF. You tell it to start at negative infinity because that's what usually does. You tell it where to stop, and if we're working with Z's, we'll put a 0 and a 1 there, and we'll be in business. There's an example with a Z-score of 1.23. Our Z's. Zero's right there, and this looks to be, maybe this would be the inflection point there. Put those numbers in. Here's where I'll put in the negative 9999 because it's easy to type. The 1.23 is where to stop. Everything up to that point gets shaded in by you. And the area, you can see even before you hit the calculator enter key, you can see that it's going to be more than 50%. And there we are. Almost 90% of the area under the curve represents the area or the probability of getting anything to the left of 1.23. If you want the right of z, draw a curve. If you've got something like this, there's our mean. Suppose you want what's to the right of this z-score. Well, the calculator, some calculators at least, don't appreciate your asking that. So you might have to do a 1 minus to get this. However, with our TI-84s and TI-Inspires, we can just tell it where to start, where to stop, and where would we tell it to stop? Well, we don't want it to stop anywhere. And what's an easy way to tell it that? Just throw in a bunch of 9s. And for all intents and purposes, that's positive infinity. Because there's almost nothing beyond there. In fact, there's almost nothing beyond 3.49. There's our picture. Use the calculator to find the area for the z-score. Get that z-score. If you don't have it, convert to a z-score. Then you can use your calculator. Now, you don't really need this. In previous days, you needed to do this. This area right here is 1 minus the area on the left. That's the old way. That's back when we were using tables. You won't need to do that because you can tell where the left bound is, the lower bound, and the upper bound, and you're in good shape. This is only if you have to use the tables. But if you want between the two z-scores, again, you're way ahead. Draw the picture, and you can see from our picture, your lower bound is going to be negative 0.75. Your upper bound is going to be 1.23. If you think of this as painting under the curve, you're going to start painting here, you're going to stop painting there, and then all of this will be a nice medium blue. So we'll put in our calculator. Normal CDF is going to give us a cumulative distribution. We want to go from negative 0.75 to 1.23. And since these are z's, automatically we have 0 and 1. Don't listen to this. What I showed you up here is all you really need to do. Next, I dare you to pause the video right here, pause the lesson here, see if you can figure out how to do this. And what's the first thing you ought to do? Yeah, are you getting the idea? These are z's, so you know zeros here. You know the number we're working with is negative 0.99. You want the area to the left, so you want the area that's in here, so shade it in. Don't be embarrassed. You wouldn't be embarrassed about getting the right answer, right? So, we want to go from negative infinity up to that point. So, you know how to get to normal CDF. You want to go from negative infinity. I'll put an extra 9 in this just for fun. I want to go to negative 0.99. we're talking about z-scores. So we're still using 0 and 1. And it's time to hit the enter key. In the area, you should get a 0.1611. If you have trouble with that, go back, watch again. If you have trouble 3 different times, contact me. Stop in the office, give me an email, whatever. Tell me what the problem is, tell me what you did, and I'll get you on track. The area under the normal curve to the right of 1.06. Okay, pause. Come back a second. Okay, you're back. Alright, here's my curve. Sure, I can do this without that. But I've actually got one of these in my head. So draw a picture still applies. 1.06 will be over here. And we want it to the right of that. So I'm going to be shading in this part. So normal CD up. I want to start at 1.06. I want to go to positive infinity, just put a bunch of 9s here. And I'm still talking about z's, so it's 0 and 1. There's your picture, and there's your area. Did you get it? I hope so. And last of all, from one z-score to another, how fast can you do this? Can you do it faster than I can write? I hope so. Did you draw a picture in your head? You want to go from negative 1.5 to 1.25. These are z-scores. So of course I put a 0 and a 1 in. And I'm ready to hit the enter key and find out what my area is between those two. And we get 0.8276, also known as 82.76%. And that, my folks, is a good introduction to normal distributions. See you soon in number 2. Bye-bye.